This is October, November 2024, paper 42 from Physics O-Level 5054. If you want to get an A, overall A, you need to score 27 marks out of 40 in this component. But if you want to get an A star, there should be at least more than 32 for this paper at least. And you can work your way back from this mark to your A star. And this actually comes down to 32 marks. I've worked my way back to this, so you need to at least score 32 out of this. For paper 1-2, they come down to 35 plus. And for paper 2-2, they come down to 60 plus. If you're at this level, then you're probably get an A star. Now, this is a measurement question. He says to measure the external diameter. He's mentioned everything else on the paper. And to make these measurements, make sure that this is also being followed. He says to round it off to near 0.1 centimeters, which means that this should be written down as 15.0, even if although we don't need to write down the unit because it's already mentioned, but as a force of habit, I generally do that, which is still a good idea instead of not writing anything. So that's why we're adding one extra decimal place over here. Plus, when you measure the diameter, what you might do sometimes students put the ruler like this, and some students put the ruler like this. For example, the student starts from a 0 mark and then measures the rest of it. Some students start with a non-zero value, let's say from 5, and then take this measurement. The best practice is to start from a non-zero value. Now, from an engineering standpoint or a scientific standpoint, the examiner prefers this method over this one. Why? Because there is a chance of zero error. It's possible that the 0 is not present at that moment, and you might be assuming that it is. And that happens during exam pressure. Plus, they say there's a chance of taking measurement from dead space. Now, this dead space is the region where you might see on your own rulers. You can check this right now after pausing the video. The ruler's edge is actually not starting from 0 exactly. The 0 mark is slightly beyond that edge. And due to usage or due to repeated usage, these edges get bent, or you can say they get broken off, which is why the examiner prefers that you start from a non-zero value, which is away from the edge of the ruler, and then take the difference. So when you do that, your value comes out as 1.5. And in terms of the wooden blocks, this is a good method in other ATP questions. You could be using this method by using a ruler on one edge, taking these points as measurements, and between them you have, let's say, 5 marble beads or 5 or 10 beakers, or any other material that you want to measure the diameter, length, size. In terms of that, you could use these wooden blocks to line them up. Now, it says, why is this important so that the blocks are parallel? You see, because this is a curved surface, it's quite highly likely that one of the blocks wobbles around on the base, and I'm of course highly exaggerating this at this point. We need to make sure that they are parallel so that the value or the measurement of h is as accurate as possible. That's what we've written down over here. Now, for this part, notice that this is the external volume, and you had measured the value of d and h already. So you just need to plug in the values. 0.79 multiplied by diameter, which was 1.5 whole square, into 15. When you calculate this, this comes out as 26.6625 centimeter cube. I would advise you to write this down at least 3 significant figures, which will become 26.7. Although by the law of minimum significant figure, this is 2 significant, and this is 3 significant, even if you consider that 0. So by general standard, we can write this down as 2 significant or 3 significant, the final answer. So I'm choosing to write it down as 1 more decimal place because one of the measurements, as he suggested, was required at a higher level of precision. Okay, the student now pours the volume in the test tube into this measuring cylinder. You're required to read the value from the measuring cylinder, and this comes out as 21. Now then he gives you the equation to calculate this. This will become 26.7 minus 21, which becomes 5.7. Straightforward calculation. He says, suggest one source of inaccuracy in the internal volume. And the most common one is that some water might still be stuck inside the test tube, or there might be, it's quite possible that not all of that has come out, or some of the water might be splashed out or might have been splashed out. So again, something related to leakage of water, or not all the water coming out. The student now uses the balance to measure this. Now, this does confuse you. It is supposed to be to the nearest gram, but this is into kilograms. But I would advise you to not use your own brain at this moment. Just take help from the calculator. So just multiply this value 0.01375 with 1000, because you know that if you want to convert kilograms to grams, you just multiply it with 1000. So this comes out as 13.75. Now, since it's mentioning to the nearest 1 gram, this will be rounded off to 14 grams. So that is how you write this down. Instead of doing this mentally, I would advise you to do this way. But again, if you can, it's up to you. Use your results in part G1 and part E to calculate this. So part G had an answer of 14 grams and part E had an answer of 5.7. You can go back and check. So we're going to use that formula, and this becomes 14 grams divided by 5.7. The answer comes out as 2.456 grams per centimeter cube. This is what we have to mention here. So this will become 2.5. The unit will be grams per centimeter cube. I was leaving this to you because you can multiply this value with 1000 and convert this into the standard unit of density, which is kilograms per meter cube, but that's your choice. Question number 2, it's an electric question. So there is an investigation based on the LED and the resistor. He sets up the circuit. Okay, fine. Records the voltmeter reading, VXY, opens the switch. Okay, so after taking the reading, he opens the switch. This is very important. In a procedural ATP question that you get at the end, this is one of the recommendations for every electric circuit that you are going to use for any investigation. Why is that? To avoid heating the wires. That's the primary target. Plus the secondary target would be to avoid cell rundown. If the cells run out, then you're not going to do any of it for the investigation because there is no power source. Okay, now he tells you in this question to draw a voltmeter connected between point. Now he mentions that it's supposed to be VXY, but there are no terminals X and Y. We can see them over here. This is your indication that the voltmeter is supposed to be connected between these two terminals. Use a ruler to draw the diagram neatly. Then he says that VXY at the current situation is this. So the scale is really easy to read. This becomes 2.5. He says record the table and notice that this is for 1 mark. So go back to the table and record this value over here. This will become 2.5. Then he gives you the rest of the instructions, what we're doing right now. Then he tells you that correct row of 2.1, record the voltmeter reading and the potential difference of VYZ. So let's go back to the table. VYZ is this, but what would be this? Okay, so so it records. We don't have to do anything right now. Okay, so calculate the value of Vx plus Vyz and record this in the table. So we are just adding these two values and writing the result in this column. So this becomes 4.6, and you can check this for the rest of the table as well. And for the last one, you can fill this automatically. So this will be 4.6 minus 2. So this should be 2.6. Again, this is an expectation. This should be in the next part, but you're doing this correctly. So we've done this, this part, and then the current, to calculate the current in the circuit, evaluated using this equation. For this current equation, picking the values from the table, let's put those values in. This becomes 2.5 divided by 270. The value comes out as 0.009259 amps, which will become 0.0093. Now, when you calculate this on the calculator, you might get a standard form like 9.259 into 10 raised to power minus 3. How do you convert this back so that it looks like, or it looks similar to the representation in the table, because that's what your goal is going to be. So on your calculators, you can press the shift button, shift plus ENG. If you don't see anything happening in the first site, you can keep pressing it until you see that these decimal places start to move from this configuration to this configuration. In some calculators, it happens in reverse. You might only be using the ENG button to represent it from this, or to change its representation from this to this. You would have to try this on your calculator. In some model, it works with shift ENG, and in some models, it works with just ENG. You would have to find it out for yourself. So in light of changing the representation, I have changed the representation over here. So this becomes 0093. And the next part is to find the resistance of the LED. So again, putting in the values only, this will be 2.1 divided by 0.0093 gives me 225.806, which I can write down as 226. Again, not using in decimal because I can see that they are also not doing this in the rest of the table. Moving on, he says that record your table in 2.2.1, and we've done that already. VXY, we have done that. VXY for 560, we did that previously. Okay, now the resistance between terminal X and Y changes, the current in the circuit changes. Okay, fine. Examine the results in table 2.1 and then comment. Describe how the change in current affects Vx plus Vyz. If you go back, you can see that the current is decreasing as a passage of time, but the sum of Vxy and Vyz is not changing. So what do you say? No change, or they're constant or unaffected. And the resistance of the LED, down the trend, the resistance of the LED is increasing, or it appears to be increasing. That's why we've written down the resistance increases. Another student resembles the circuit. Okay, fine, 2.1. The LED does not light up. Now, this has been a common occurrence in the past papers. He has been asking you these questions related to circuits, be involved with a diode and some other things. He says just one error the student has made while assembling the circuit. He says everything is fine. He tests the components and finds that the power source is producing an EMF, which means power supply is working fine, and there is no other component that is broken. Everything else is working, but still there is no current, which means that in the circuit, by mistake, if we come back here, the general understanding is if you want the diode to switch on, or if you want the diode to allow current to pass through, then this terminal should be connected with a positive one, which means that the diode's arrow, or the direction of the arrow, should match the direction of current. If that is the case, the diode will allow the flow of current. But if it's not the case, if you connect the diode in the wrong orientation, then there will be no current. So in this case, what the student might have done is, instead of connecting the diode this way, he might have connected the diode this way, in the opposite direction. So when the current is trying to flow, the arrows are opposite, the current does not flow. This is just a trick to remember if the diode is forward biased or not. This is not a scientific method, but yet works in some situations. But if, for example, the diode is connected the right way around, it's quite possible the student might have connected the supply voltage at positive and negative in the reverse order, because he's assembling the circuit again. And when the current tries to come from this side, the arrow of the current is opposite to the arrow of the diode. So there will be no flow of current. And as a result, the readings on the meters will be 0. Again, the arrow method is a non-conventional, a trick to remember the diode function. It's not scientific. All right, so in this case, we explained the situation, telling them that the diode or the power supply is connected the wrong way or the opposite way, or the voltmeter is series. Now, this is interesting. Another answer in the marking scheme, the resistance of the voltmeter is infinite. It's quite possible that since there is no ammeter in the circuit, the student might have connected the voltmeter in series in some sense or by mistake. Voltmeters have infinite resistance, which means it is very, very high. No matter how high voltage you provide, they will not deflect. That's how highly resistive they are. That is why they're connected in parallel, because they don't draw any current and still give you some reading. But anyways, so by mistake, the student might have connected the voltmeter series, which is why there is no current, because all the voltage will be taken up by the voltmeter itself. But the voltmeter is behaving like a resistor in those circumstances, which is what an extra answer would be. Name that draws a symbol of single device that can be used to change the current. Need to connect different resistors across the terminal X and Y in the circuit 2.1. So the name of the device, as you might have guessed this already, is the variable resistor. And the symbol of the variable resistor looks like this. Now, just a reminder, for a thermistor, it looks like this. For an LDR, it looks like this. So just be careful about your symbols. And a fuse looks like this. A fixed resistor looks like this. All right, question number 3, lens question, light question. Again, a very, very common question. You can read everything else in your question book. He says make the measurement to the nearest 0.1, record the distance x, and write this down here. So this will be 5.1. Now, one thing you might notice during your own practice at home, if you've gotten this printed from someone else, let's say a local bookstore, you would realize that these magnifications or the printing that they do might be on a bigger or a smaller paper than standard paper. Your readings might be off by a few centimeters. Let's say some of you might get 5.3, some of you might get 5.5, some of you might get 4.9, 8, 7, 6, or whatever. But that is due to the printing problem. That's not due to the Cambridge. That's the person who printed the paper, who printed it, actually chose a different scale, which is what causes this problem. But no need to worry about that as long as you remember that you're using the displaced screen method. You're starting from a non-zero value, let's say 3, and then go up to another non-zero value, let's say 15, 17, 20, whatever that may be in that case. Okay, so he says that it's 1/3. What will be that in reality? So if it is 1/3 scale, then in reality it will be 3 times longer. So this will be 5.1 into 3, making this 15.3. It's a scaled down version of a real life scenario. The student arranges until a sharp image is probably seen, a triangular object, let's say like this, from the sides, switches on the lap, places it here, and positions it until a triangular object is formed on the screen, measures that image distance, and then gives us this equation. Okay, fine. He mentioned u himself. He mentions u. He mentions v himself. Now he wants you to calculate those values. So simply put, that would be 20 plus 60.5. No hassle, no problem. So 20 plus 60.5 and 20 multiplied by 60.5. This becomes 1210. This becomes 80.5. Now the next, I think, add appropriate units. So if you add units, this will become centimeters and this will become centimeters squared. How do we know this? Because when you're just adding them together, the units are not being multiplied. It's as simple as that, that if you add, let's say, 5 kilograms of apples with 3 kilograms of apples, the total mass stays the same and the unit also stays the same because you're not multiplying them, you're just adding them. Similar case with length. If you're measuring length in 2 pieces, for example, for a room, you might be taking the measurement twice. For example, you might be taking measure up to this, then this, then this, and then you try to add all of these measurements together, which again leads to the same unit. That's why when you're adding them together, this was centimeter, this was centimeter, so there's nothing wrong with this. The unit will be the same. But in this case, you're multiplying both of them, and if you multiply something with centimeter, this becomes centimeter square, which is why the unit will be centimeter square. So keep an eye about these parts in the next past papers, in the next paper that you're going to attempt. Okay, so these things are complete. Now we're going to fill in the data over here. So this should be 81. Why? Because the rest of the column has been rounded off. So we have to be careful about that. So this will be 1210. As we can see that they are also doing the same thing with the larger values. We don't have to round it off or round it up to 3 or 2 significant figures. He's not taking care of that. We're just going to follow what the rest of the table does for the sake of uniformity. Moving on, this is how we represent our data. Then he tells you that you don't need to start the graph from the origin. Thank you, that's a help. X-axis has to be UV, U plus V, and UV has to be Y-axis. So the first thing you're going to do is label the axis. So you will simply write down this is UV / centimeter square, and the X-axis would be, with the bracket probably, U plus V / centimeters. Don't forget that. It's really important. And now you have to count boxes. Now, what I generally recommend is count the boxes that you have access to. So 1, 2, 3, 4, 5, 6. Similar on the y-axis, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 boxes. Now this is y-axis. This is y-axis, where I have 8 boxes, and this is x-axis, I have 6 boxes. What I would generally recommend is to use the largest value and then divide this with 8 to find out what each box may represent. But then the problem would be that the scale would be too small. The graph would only be accessible or would only be existing in this upper part. Let me zoom out. It would only be existing on this region of the graph. We need to cover more than 50%. Now, since he tells me that it has to start, or you can start it from a non-zero value, then I would take advantage of that and I will consider that probably 62 is my smallest value and 81 is my largest value. So I should start from 60 and go up to 80 somewhere around here so that at least my whole graph is covered. Now, in light of that, when trying to do that, You can do this mentally, okay, and try to find a good scale. So what the scale that I have chosen is starting on the y-axis with 900, and then going back to 950, then 1000, and so on, with up to 1300. And on the x-axis, I have started from 60, and at this point I'm coming at 90. So this will be 65, this will be 70, this will be 75, 80, and 85. Now my smallest value on x-axis starts from 62 and goes up to 81. So I'm covering at least this region of data, this region of the graph. Let me zoom out a bit more. At least this much region is being covered because of the x-axis. And the smallest value I have on the y-axis, sorry, this is going to be in the opposite direction. That is y-axis, this is x-axis. The smallest value that I have is 933, and the largest one is 1210. So 933 will be somewhere along this line, and 1210 will be along, I think this is 1250, the last one. So 1210 will be around this line. So the actual region that we've covered up is this one. We're covering more than 50% of the graph area, which is a good idea, which is a good thing. So your scale will be accepted. Again, you can try with a different scale. It's totally up to you. They don't mind. Okay, so what I have done is drawn the graph myself and added that in 3 stages. And let's zoom in and see what the examiner might be expecting. So notice that the coordinates that I have plotted, taken from the table, they are really, really small. They are not even going beyond half a box, which is allowed in the Cambridge examination. Notice that if I draw a graph like this or a coordinate like this, be careful. If I fill this box or small box completely, zoom in a bit. I think I can't zoom in anymore. So if you fill this box in, this is wrong. This will not be considered a coordinate. A coordinate is considered that dot which is within half a box, which means that if I were to color this area, this tiny box, a coordinate should not be larger than this, a fourth part of that smaller box. So you can just pinch your pencil at a certain point, or just pinch your pencil at this point, and you're good to go. Once you've drawn these coordinates, your graph should look something like this. In the first case, this is what your graph should look like. Once you've done that, you can now move on to drawing the line of best fit. Now, when you draw the line of best fit, this is what it's supposed to look like. Your line might be a bit different. You don't have to force them to go through the origin. It happens to be in my case. Your line might be slightly above or below. It's completely fine. Now, once you've drawn the line, also make sure that the distance between the points above and below the line are equal. Try to take most of the points on the line. There's one point just slightly above the line. I could have moved this line a bit further to the upper side so that this line comes close to this point, goes a bit away from this line, and comes close to this one. I could have done that. That would also be considered a line of best fit. That's completely fine. There is always a wiggle room in these situations, in these scenarios. Once I've drawn the line, then I highlight the points by drawing cross on them. I draw the cross later in the last stage. Then for the gradient, what I'm going to do is choose the points that are furthest away as far as possible that are on the grid. So what I have done, if I zoom in, what I've done is I have selected a point deliberately which crosses the coordinate itself so that I don't have to guess. For example, if it crosses from the center, it's a problem. I wouldn't prefer that coordinate. If it crosses like this, again, it's a problem, will cause definite problems in counting. So I've selected a coordinate that is exactly crossing this point, which will be easy to read. Same thing I've done if you go down to the line, same thing I've done over here. I've selected a point which is exactly accurately on the dot. I could have selected this point equally as well. It's your choice. But again, keeping in line with the exam pressure, exam time, you might not be able to see some coordinates better than the other one. But the main focus is of this exercise or of this process is to choose your line at least more than 50% of the rest of the line. For example, if I consider this whole line to be one single entity, which it is, this is one single line, my gradient coordinates should cover at least more than 50%. So if these coordinates, how far they may be, are more than 50% of the total line, then I am in the green zone. I'm good to go. This is why I would choose, again, as a student, I would be looking at on the larger side, on the upper side for one coordinate and on the lower side for the other coordinate. Do not use the coordinates from the table. That will be wrong because these coordinates didn't come on the line. They are not on the line. They are represented by the best fit line, but they are not on the line. You're looking for the gradient of the line. So you will choose points from the line, and then how do you tell the examiner? As you might see in the question papers, he is so adamant now to show your working. If you see, now he's very, very clear about showing your working. Now this is part of the showing your working. Again, some teachers recommend not doing this. Some teachers think it's fine not to do this, but I recommend doing this. So draw this triangle, dotted triangle, that represents the coordinates that you have selected. The examiner would know that this is what you're doing with your work. And then don't forget to write down those coordinates over here. Read them correctly, read them carefully, so that, and then mention them for the examiner. So this is 63.5 for me, 955. The other coordinate is 82.5, comma 1260. And then I show the examiner that I'm using the gradient formula. So the gradient equals to, and I can use the values directly. So this will be 1260 minus 955, show your working. And then 82.5 minus 63.5. This comes out as 16.052. And I will write this down as 16. And if you go to the marking scheme, it says the range could be 15 plus minus 3, which means that it could be more than 15 up to 3, which means it can be 18, or it can be less than, or 3 less than 15, which would be 12. Yeah. So this is the range of answers you might get with the gradient. So you can see there is a lot of room for error. Okay. All right. So that's how you draw your graph. That's how you show your working to the examiner. This is part F, again, a really important part in your coursework. And this will be a repeated part, so keep that in mind. Okay, so he says that within the limit of experimental accuracy, which is 10%, how do you know that the thing that you calculated in part E, part A2, are within range? So how to present these calculations? So you will write down that in part A2, the F that you found was 15.3. Go back to the paper and revisit. And in part E, you found F equals to, which was the gradient in my case, equals to 16. How do I know that the person who presented this hypothesis, or who's making these claims, that they're numerically equal to the focal length, or they're numerically equal? Should that person's hypothesis or recommendation be accepted, or should it be rejected? What does the science or the physics say about that? Which scientist results, or whose scientist result would be accepted as acceptable or fairly acceptable? The criteria is 10% of each other. How do you do that? Completely your choice. You can either take 10% of this value or take 10% of this value. Previously, I used to take 10% of the larger value so that it can give me a larger range, and my conclusion could come out as yes. But you don't have to force your answers like that. That's just a trick to do that. So right now I'm going to show you with a smaller value. Does that still come out as a yes or no? You will have to justify your own results. You might get a no, you might get a yes. Don't be scared about writing down a yes or a no in these circumstances, because it really comes down to what you found out. That's your truth, and you would have to own it. So in this case, if you multiply 15.3 with 10%, your answer comes out as 1.53. Now this is actually plus minus 1.53 of 15.3. So then you go on to writing down the range of values. That will be 15.3 plus 1.5. and then 15.3 minus 1.53. So your range comes down after adding 15.3 with 1.5, comes out as 16.83 in my case. And the smallest value that you're supposed to get according to my case should be 15.3 minus 1.53 as 13.77. Now you applied the test on part A2. You designed the range from part A2. The test would be implemented on part E, on the other value. Does this fit in this range? So yes, my range goes from 13.77 to 16.83. Does 16 fall within that range? My number line starts like this. So it's 13.77 up to 16.83. The other value 16 somewhere along this line. Does it come within the range? Yes, it does. So my hypothesis, or the person's hypothesis, is correct within the limits of experimental accuracy, or within the limits of 10% limit experimental accuracy. As a scientist, you can put more stringent conditions on yourself or on your results. You might agree with 5%, but for O levels and A levels, this will stay at 10%. When you go to higher levels, definitely every scientist, every lab will define what is the level of tolerance they can accept. It generally comes down to, let's say, a 2% or 3%, that if the error is beyond that, then we don't agree with your hypothesis or whatever you're trying to say. So the statement would be, in this case, that the part E answer, which is F equals to 16, is within range of 10% experimental accuracy. So I agree. I agree that F is equal to 16, or the gradient is representing the focal length. So you just agree with the person who gave you this statement, who gave you to test it out. When measuring the object, the image distance with a meter ruler, it is important to avoid the line of sight parallax errors. State how the student can avoid that. So he's mentioning that we need to avoid parallax error, but how do you do that? So view the ruler from right angles. Now, this used to be a 2-mark question, but what the students would generally write down is avoid parallax error. That would score just 1 mark. But it's always about the how to do that. So the complete answer usually used to be avoid parallax error by keeping the line of sight perpendicular to the ruler. Which half of that has been done already in the question. So that's why you're left with just 1 credit. So you just explain to the examiner, view the ruler at right angles, or view the ruler perpendicular, or keep the line of sight perpendicular to the ruler. Many ways to say that, but that's the gist of it. Describe a technique the student uses. Now this is again a repeated part. This is a repeated part. This is a repeated part for lens questions. This is a repeated part for every question that you will encounter in ATP. This has been a common occurrence now. He says how to get a sharp image. So the general answer, that's what you would do. That's what you guys do with your own mobile phone cameras. If you use them on manual mode, they're trying to autofocus, right? So the lens moves forward and backward until it finds the sharpest image or sharpest location. That's what you're going to do manually. So you move the screen back and forth until a sharp image is seen on the screen. That's what you do. Question 4 sometimes serves as a kryptonite for some students, but don't worry. So always pay attention to the first statement. The rest of them can come later, but always pay attention to the first one. This first statement clears out the intent of this investigation. Don't ignore that. And I understand what some students do. Directly jump to what you need, directly jump to what we need to plan, and then start writing down their answers. Don't do that. You need to understand what the examiner is trying to do. So now you are on a guided path that what is the investigation supposed to be. So don't avoid the very first statement of this question or these type of questions. He says water is heated from room temperature to the boiling point in a glass. Now comes the task. Plan an experiment to investigate. You will investigate. You will search. You will find out what the time taken for the water to reach boiling point. Okay, fine. That's what I'm testing. But against what? Does it depend on the diameter of the water surface exposed to the air? Does it depend on the surface area? That will be a higher tier question, but right now he's narrowing it down to diameter only. What he has given you is supply of cold water, different glass beakers, Bunsen burner, a measuring cylinder for the volume. What he wants you to do is plan, or your plan should include these points. Now these are 5 points. Generally there will be 1 less than the marks of the question. If you just answer these questions in order, you are done. You're set. You will still get 5 marks out of 6. If you want to get 6 out of 6, then you need to add some more details that sometimes maybe is not even the marking scheme. So any other apparatus do you need? Do you need something more? There might be something related to the temperature. You might need a thermometer. You might need something else. But if you notice, you're trying to measure time. But is that mentioned in the list of equipment? It's not. He has given me the liberty that you may use any of the common laboratory apparatuses, and stopwatch is one of the common ones. So that's what I would suggest. Now, before we move on to the account, I suggest what the equipment I need, the brief description on how you're going to do that. So simple method. What are you going to do with your hands? You're going to place something on something, you're going to measure something, you're going to perform some action. He's looking for action in part number 2. Part number 3, the variable you will control. What is the thing that you're not going to change so that the test becomes fair, or it is still a fair test comparison amongst all of them? And that's what we do in physics. For the sake of example, if we had the equation F equals to ma, if you're trying to experiment force being proportional to acceleration like this, then you will definitely make sure that the mass is constant because you're not studying that. So in this case, since we're studying the time versus the diameter of the beaker, I would have to eliminate all the other variables and trying to make sure that everything else remains the same. So what would that be? In my case, that would be the mass of the liquid, or the initial temperature of the liquid, or the volume of the liquid. Don't write down amount of water. Amount doesn't mean anything. Refer to either volume or mass for a substance. That's what I would try to control. And one more intelligent key would be to control the amount of heat coming from the Bunsen burner. This is with alcohol, the spirit lamp, but you can, if you're using Bunsen burner, then definitely, I think he has given you a Bunsen burner. Yeah, the Bunsen burner is present. So controlling or keeping the heat, or keeping it at a constant heat coming from the Bunsen burner. So that would be this, a result table to record. Now, this is what sometimes students get wrong. You don't have to fill in the values, just have to show the headings and what you're going to record. So if you go back to the question from the examiner, this is what you're supposed to do without the values. Just show what you're going to measure with respective units and leave the rest of the table empty. That's what he wants to see. How would you tabulate your data? How would you draw conclusions? Because you need a table for that. So I will show you how to do that. And then how will you process your results to draw a conclusion? What are you supposed to do with the collection of results? You get a table, you get a graph, or you want to make a conclusion. What do you do with those values? Let's go back to the question that we've done before. So a similar question was in this part, right? I think it was the previous one, the diode one. Yeah, this one. So he asked you the same question again over here. Over here. He wanted you to use the table to describe what's happening. You use the table to describe that down the trend, the resistance is increasing. You picked that up, right? Something similar is expected of you from these questions. That how would you use your results to process or draw a conclusion? That's about it. You may wish to draw a diagram. I would advise you to draw a diagram. Don't leave out any other details. So for example, if something is missing in your account, they would definitely refer to the diagram. But again, it should be a labeled diagram. Okay. So this is a gauze and this is the beaker. This is, let's say, in place of spirit lamp, you can draw a Bunsen burner. You're completely capable of doing that. This is your account. Let's go through all the points versus what we've written down. So we will get straight to the point, no extra details, just plainly answering these questions in order. So use a ruler to measure the diameter. Okay, good. And stopwatch to measure the time to reach the boiling point. Okay, fine. We've answered the first question. Repeat the same method for other beakers. Good. That is what the method is about. That is what he's asking you. Describe a brief description of the method. What are you doing? So repeat the same method for other beakers. Now this is your answer number 2. For every beaker, do the experiment twice. Now this is what the added detail is about, which sometimes might not be in the marking scheme. Do you have to repeat the experiments? Yes, you always do a repetition of the experiment with the same variable so that you have 2 values. So this is an added detail, an added bonus. Every beaker twice, and then once you've repeated the experiment, what am I supposed to do? You're supposed to calculate the average of those 2 repetitions or those 2 results that you were trying to find out. Okay. Time to reduce the inaccuracies. That's why you're doing that. So mass, volume, initial temperature of water should remain fixed or kept constant. This is your third question. You can choose any one of them. You don't have to write all of them. This is just an option given to you because I'm teaching you right now what you can put in here. Should remain fixed or will be kept constant. Try to ensure the constant flame from the Bunsen burner. Again, point number 3 being enforced from the point of Bunsen burner. Point number 4. How do you draw the table? Okay. So serial number generally comes in. Diameter, again, what you want to measure is in words. Don't write down D/centimeter. Again, you will see that in the marking scheme, he says that you can use D, but if you want to use just letters, this should be explained in the account. So if you say that measure the diameter D and stopwatch to use measure to measure time T, if you've used these letters in your account, then definitely you can write this down like this. But again, to avoid any confusion, I would recommend, even if you've done this, always use the words to avoid any confusions. Okay, so diameter being in centimeters, time. Now, you might see that there are 2 times in here. Why? Because I suggested to repeat the experiment. Okay, there should be time 1, time 2, then taking the time average. For example, this is 15 seconds, this is 16. I add them together, divide them by 2, and take the average time and then plot the graph. This is 4 points. Then the 5th point. What do you do with the conclusions? I will draw a graph of diameter against time to draw my conclusions. Or I will observe the table, look what the trend is, and then explain or give my explanation. Now, these are just 5 points, 5 marks. You get the extra credit for adding more detail. You get the extra credit for suggesting more than one constant. So there are plenty of places where you will get the extra credit because this is a 6-mark question. There are 5 questions you address, right? This is the general technique of answering these questions, and I hope the technique remains the same. The account can be different. And you can see that these are just 5 or 6 lines. You are done with your explanation. Don't go into more detail. Just try to answer these questions, and it will always be simple. You will see that if you go through at least 5 or 6 procedural questions like this one, the question before the last question in an ATP, if you go through the marking scheme, looking at the question paper and directly going to the marking scheme, trying to work your way around it, you will see that there is a pattern, and that pattern is this. It's simple. It's straightforward. No need to worry about that. So I hope you've learned something. I'll see you soon.